Okay, welcome back to the part 2 in this lecture about journal bearing dynamics. This time we will discuss the eigenvalue problem and then also discuss and then also describe mathematically why a journal bearing can become unstable, and then later also we'll discuss how to solve stability problems to avoid them already from start. But we always want to put some mathematics on this to do the analysis, and in order to do so we will solve the so-called eigenvalue problem. That is a little bit to find what we are a little bit, well, maybe not correctly, but we normally say we find the critical speeds of the bearing. You remember that the bearing oil film can be described by linear dynamic coefficients, and that there is a cross coupling between x and y directions. And if you set up the equations of motion for the journal, so m is the mass of the journal, and mass certain amount of the journal, you take the stiffness and you take the damping here and you write it in matrix form, it becomes something like this. I think you recall this from dynamics courses maybe, but you remember in one dimension it's only x, but in this case it's the journal can move in both x and y directions. That's the reason why we have both x and y here, and we have the speed. This is the velocity vector then, and this is the acceleration vector of the journal position. We can simplify that by putting everything on the same side, and we can since this is a linear system of linear equations, we can introduce the general solution to a differential equation of this type, and that general solution is x multiplied as an x naught, an amplitude multiplied by e to the power lambda t, where lambda is a complex number in this case. Normally, if it had been if in the normal 1D case, you remember you can use a sinus or cosinus function here, but in a more general case we use this exponential function way of writing it. So you can describe both the x motion and the y motion with this same type of equation. And this lambda, as I said, it's a complex number, and that number is called the eigenvalue. And the eigenvalue has then two parts. It's the real part and the imaginary part. The I is the imaginary unit. And for conditions that if you want a stable operation, then this real part must be 0 or at least less than 0, because if you go back here, if the real part is more than 0, this will grow exponentially. It will be bigger and bigger motion. So in a short time you will have a very big amplitude, and if the journal has a big amplitude, it may crash into the bearing surface. So the stability condition is that the real part of lambda must be less than 0. That means that it's positively damped. If it's a negative number, it will die out after some time. So if we now are looking for what we're searching for is actually the limit where instability occurs. That means that alpha we can set it to 0, exactly to 0. So the eigenvalue becomes simply I multiplied by omega. So omega is actually a frequency. You can look upon it as a frequency. And now putting this into the x and y expressions, it becomes like that, and you can find the derivative to that, to the speed. You get a speed vector. So that's simply I omega multiplied by x and y, and again you can do derivation one more time and you get the acceleration, and then you get rid of the I, but you remember I with a power 2, that's -1, so you get the minus sign here instead. So now you have the x, the position, the speed, and the acceleration. So put that into the equation of motion now, and then you can simplify it, and you can get the amplitudes out here and a simple matrix with 4 terms here. Note you have a complex number here. There are complex numbers in all positions in the matrix. If a system like this has an interesting solution that is called non-trivial solution, that means that the determinant of the matrix must be 0. You need to look this up in the dynamics courses. I'm not telling you more than this here. But in order to get this non-trivial solution, I mean, a solution to this equation could be 0 amplitude here, and that's pretty uninteresting in our case. But so for our cases, the determinant of the matrix must be 0, and the determinant of a 2x2 matrix is simply that term multiplied by that term minus that term multiplied by that term. And if you do that, I haven't shown it here, you will get a long equation with 2 parts, one with a real part and one with an imaginary part. And if the determinant should be 0, both parts must be 0, so we can split them into 2 equations then. And this is the real part, I believe, and that must be 0, and this is the imaginary part, it should also be 0. Now you see that what's inside here, it's a mass, it's a vibration frequency, it's the stiffness and the damping terms. Okay, let's move on. Now we can introduce the non-dimensional C's and K's, the dampings and the stiffness. Again, they look like this. And we introduce them into the equations, and we simplify a little bit, and we find that, look here, we have a term here with only C's and K's, non-dimensional C's and K's, and we call this gamma, capital gamma. And so this can be determined from the diagrams I showed you in part 1, in the non-dimensional graphs with versus eccentricity. So for a given bearing geometry and bearing type, this gamma is a function only of the eccentricity. And we can also put this into the first equation, and again we end up with some C's and K's here together with a gamma, and let's call that F squared. So again, both F and gamma are only functions of K's and C's. That means function of eccentricity. And here, look here now, the omega is a vibration frequency, and the capital omega is the operating speed of the journal, that rotational speed of the journal. So this omega is simply the vibration frequency when instability occurs, and all these terms are functions of eccentricity, which can be determined by using the diagrams I showed you in the first part, the simple design charts. Okay. Now, again, the relationship between omega and capital omega, or the critical operating speed, is then this F factor. We can put this into the other equation again, and we get this relationship that mF squared multiplied by the critical speed squared is the statical load divided by the static load divided by clearance multiplied by the gamma. That means if we only search for the critical speed, that the critical speed after some simplification, and now we assume that the load is just it's just due to the mass of the rotor. Then the critical speed simply becomes like this. Remember again, this is something we can determine from the diagrams, and G is the acceleration, mass acceleration, or gravity acceleration term, and delta R is the clearance. So pretty simple. So now we can do this because we have these gamma and f. We can compute this gamma and f for a certain bearing, and the curve will look something like this. So depending on the eccentricity, the rotational speed, the critical speed follows this blue curve. So at low relative eccentricity, it's a pretty constant critical speed, while at higher eccentricity, the critical speed increases. So from a stability point of view, so below here, if your real operating speed is down here, that means that you're running under stable conditions. But if you're up here, you run under unstable conditions. So you shouldn't run at higher speeds than this critical speed. If you can operate at high eccentricity, you can definitely operate at higher speeds. The disadvantage with that is, of course, that you operate at high eccentricity, and high eccentricity means small film thickness, so you run at very thin oil films, so you may have other problems with that. Could be wear problems, or you could have vibration problem causing contact anyway. But it's good to know that the critical speed increases here. Now, when we add our own the journal speed, then it follows the curve like this. As I said in the beginning, in the first part, at no speed, it starts at eccentricity 1, and then as the speed increases, the eccentricity decreases, and eventually it reaches the same speed as the critical speed, and it enters into the unstable region here. So the bearing always follow this curve when it increases the speed. So that's the limit for stable operation. And when it comes up here in the unstable regime, it will start vibrating with higher amplitude, and then eventually it may crash into the surface of the bearing. Then the amplitudes become bigger, and the theory of linear dynamic coefficient doesn't really hold, but still, I don't recommend you to run at higher speeds than this. And a funny thing is that if you plot the f factor, or 1 over f maybe, you will see that it's approximately 2. So the critical speed is double the Whirl frequency if you run at low eccentricity. And this is the reason why this phenomena is sometimes called a half-frequency whirl, because in measurements of rotating machinery, they have suddenly seen that the vibration at a frequency half the operating speed occurs, and that's a sign of unstable operation, and you should stop the machine immediately when you see that, because that is very dangerous. It could definitely destroy the bearings, and then also destroy the whole machine. Okay, how to avoid them then? How can you change something to avoid this problem if it occurs? Well, it depends a little bit if you have a lightly loaded or a heavily loaded journal. If you have a lightly loaded journal, then that means that you run into the unstable regime here on the flat part of the curve. It doesn't really matter, even if you increase the clearance, for example. That means that you lower the critical speed, even if you know that if you increase the clearance, that means that you move in this direction, you increase the eccentricity. But if you don't increase it sufficiently much, you just move the curve in this direction while you also decreasing the curve itself. So the critical speed comes at lower speed. So that's a negative effect to do that. But if you are here, up here, increasing clearance could be a positive thing, because then you take advantage of the shape of the curve here, and you come into the high eccentricity regime where you can run almost stable at any speed. But you must be cautious here that increasing the clearance is not always a good thing. Another way to solve the problem is to actually decrease the bearing length. That means that you make it the width less wide, and that means that you operate it also at higher eccentricity. You can see that from the diagram here. And that means that you also come into this more stable regime. On the other hand, you run at higher eccentricity, and the bearing runs at higher load. But increasing the bearing length is definitely a negative thing. If you do it here in this region, it doesn't really matter, because you just move along this curve. And it's the same thing with the increasing viscosity. If you increase the viscosity, you see here it has the same effect as increasing the width. You will decrease the eccentricity, so you will run into this part. On the other hand, you may decrease the viscosity. That could have a positive effect, but then you have the risk to operate the actual bearing operation itself. And you should also remember that if you have no load, you are always running at zero eccentricity, and you will directly, as you increase the speed, run into the unstable condition. So a bearing with no load is always unstable. And that's the reason why the vertical shaft has a problem, since there is no load applied there. This is could be a typical steam turbine, at least what is typical steam turbine at the time I was working for a steam turbine company. And in this case, it's a high-speed steam turbine which drives a generator via speed, and then a low-speed turbine here. And in this case, 10,000 RPM, a machine like this can definitely come into the unstable regime, because the rotor is pretty slender. It's a long rotor with a small diameter. So this actually happened a number of times when I was working with these problems. And how do you resolve it? Well, there are a number of ways to do it. You can change the geometry of the bearing in different ways. And a traditional way is to use an elliptical bearing or lemon type bearing. I don't recommend that. What we saw at that time, we saw that something called the offset halves was better. And that means that you actually move the upper or lower half relative to the upper half a little bit, and that makes even at no load, the bearing, or both halves of the bearings, has some eccentricity. And as you remember, higher eccentricity is better. So this, you have some kind of preload on this bearing that makes the eccentricity higher, and of that reason this bearing is less prone to stability problems. Still, stability problems may occur, but at higher speeds. Another way to completely avoid stability problems is to introduce something called tilting pad bearings. That's, you have in this case 5 pads, and they are separated from each other, and they are free to tilt. They can adjust themselves. They are schematically here, they are tilting in a pivot point here. And this type of bearing has almost no cross terms in the stiffness matrix. So the KXY and the KYX could be set to 0. And if they are 0, you don't get any stability problems at all. A bearing like that looks like this in reality. So these were the typical ways to solve it. Another way, if you have still extreme cases, you may introduce some extra damping. And then you can introduce some extra oil film outside. That is called squeeze film dampers. And that is used also for rolling element bearings, because rolling element bearings, they don't have any good damping in themselves, so you need add some damping, and that is sometimes done in a jet engine, for example. In a steam turbine with the plain journal bearings, you can also add a squeeze film damper. So you have actually two oil films. You have one oil film that is the bearing itself, and then outside that bearing you have a stationary oil film, which is just a damper. So the whole bearing bushing here is swimming in oil, and when it wants to move, it doesn't rotate, but it can vibrate vertically or horizontally, and when it vibrates, some damping is you get some damping from the oil. You need also a mechanism to center this damper normally. You want it to be concentrical, and so normally you have some spring system here to adjust it to be in the center, and these springs must then be soft enough to not cause any other stiffness effects. So that's a kind of some ways to solve these problems. So, and just to finish this lecture, to say a few words about extremely high dynamic forces, like in an engine. Then inside the bearing circle you may see motions like this. The journal moves more or less the whole circle, inside the whole clearance circle. So this condition of 10 to 20% of the clearance doesn't hold anymore, and then you can't use this type of theory, and you must solve Reynolds equation, the time-dependent Reynolds equation, and couple that to the structure dynamics software of the engine. So that's a pretty complex analysis, but it's normally done nowadays by companies developing combustion engines. So that's all about bearing dynamics. Thank you very much.